I'm going to start with a little warm-up activity just to make sure we're all like awake. It's still early in the day. So here's what I'm going to do. I'm going to put up some formulas, and you're going to tell me when these formulas are true. All right? Ready? Good? Okay. When is this formula true? A and B are both true. How many ways are there of making this formula true? One way. Perfect. Good. Okay. How about this formula? So 2 ways? 2 ways? 3 ways. 3 ways. Good. Okay, nothing gets past you. Excellent. Okay, so 3 ways of making this true. How about this one? 0. Excellent. Good. How about this one? All right, it doesn't matter. You get the point, right? Okay, so what am I asking you to do? I'm asking you to be a human satisfiability solver, right? Given a formula, tell me whether the formula can be satisfied by doing a truth assignment, and also sometimes how many different ways of doing it. And the point is, there are many ways of doing it, okay? So you've all succeeded at being human sat solvers. Now, why do we care about this problem of satisfiability? Because it turns out lots and lots of interesting technical questions can be turned into satisfiability questions, okay? So I and many other people have built a whole bunch of tools that take interesting systems questions and turn them into satisfiability questions, send them off to a solver, such as yourselves, right? Get the answer back and present it back to the user in a domain where they can then act upon it, okay? So we build tools for security engineers, for networking engineers, and so on. All right. Now, SAT formulas are kind of boring and annoying to look at. I like to interface to SAT with better tools than that. One tool I particularly enjoy is a tool called Alloy, built by a group, Daniel Jackson's group at MIT. And what I'm going to give you is like a very, very brief feel of what Alloy feels like. And then that will be the point of departure for the rest of the talk. Okay? So in Alloy, I write down specifications. I don't expect you to read the code. I just want you to observe it's got like, curly braces, so it's obviously code, right? Like if it's got curly braces, it's good, right? So it's meant to be sort of like vaguely Java-ish, evoking Java-ish stuff. And here, this is a specification for a binary tree, okay? Or at least a purported specification of what a binary tree is, okay? And this is the specification, and classical verification, like going all the way back to, like Dijkstra and Hoare and people like that, is you have a specification, and then you have some properties that you want to know whether they're true or not, okay? So you write down some property statements, and then you can press a button. In this case, there's a button called execute. You press the execute button, and it comes back and says true or false, okay? And in fact, if it's false, it says here's a counterexample, and you can click on it, and it shows you a picture like this. Now, is this a binary tree? Why not? If it's not a binary tree, tell somebody, audience, come on.
Multiple roots.
Multiple roots, okay. Other reasons? Cycles. Any other reasons?
Shared nodes.
Yeah, shared nodes. Okay, so the point is there's lots of ways this is not a binary tree, right? So you get to see this counterexample, and hopefully you can go fix it. So for example, if I go and fix it and I click run again, it comes back and says no counterexamples found, okay? Now, this is the subtle part, which is no counterexamples found doesn't mean you have a binary tree. It just means up to the level of specification you've written, you are good to go, okay? And if you talk to a verification person, and I know there are some people in the room, so I'm purposely not making eye contact with them to avoid embarrassing them, right? You ask, where did you get these properties from? And they'll be like, oh yeah, that's a hard problem. Like, anyway, moving along. Okay, and the HCI people, of course, hopefully will stop and say, no, you can't move on from that. Like, that's the heart of the whole enterprise here, right? In fact, these tools, the verification tools, have the sort of fatal flaw. If you can't articulate any properties, they will not do anything at all. They'll just sit there and say, like, I don't know, you haven't told me what to do, okay? So there is an interesting question, an underlying question here of how do we even figure out what properties we want? What do we care about? One of the reasons I like tools like Alloy, tools that work on SAT solver. Again, for the technical people here who are like that kind of technical, I'm talking about model theoretic tools as opposed to proof theoretic tools. We can talk a little bit about proof theory at the very end. If those words don't mean anything to you, you're golden. If they mean something to you, that's the domain I'm working in for now. Okay? All right. So the nice thing about a tool like this is you can say, look, I don't have any properties yet. Can you just show me some examples? Just show me like instances. And it says, sure, I can give you an instance, and it gives me an instance like this. Now, is this a binary tree? Why not? I'm going to argue that there's at least one more reason why this is not a binary tree. Can you spot it? You spot it? You gave me like 3 reasons last time, right?
Pointing to parent.
Huh?
Child. Pointing to parent.
Child pointing to parent. Yeah, that's a kind of cycle. Yeah, another reason.
Right and left are the same.
Yeah, right and left are the same. You can't, that's not a tree either, right? So there's all sorts of ways it's not a tree, right? And the hope is that by looking at these kinds of examples, we can start to articulate the ways in which this violates our expectations, which you then codify into properties, which you can then use for verification. Okay? So that's one of the reasons these kinds of methods appeal to me, is there's a more bottom-up inductive way of thinking about things rather than the sort of top-down, you must know what correctness is, and if you couldn't specify it, that's your fault. Okay? All right. So this is a very quick sense of the kinds of tools that I'm talking about right now. Okay? I'm going to now do, for the rest of this talk, I'm going to focus on 4 aspects of this. The first is, what am I computing? When I press that execute button, what happens? What do I get as output? The second is, what do I show? The third is, how do I show it? And the fourth is, how do I describe systems? Okay? Now, from a visual interface accessibility point of view, I apologize, there's a little bit in this talk that's not entirely accessible. I'll do my best to articulate it as we go along. But 1 or 2 things I'm gonna have a picture and say, what do you see? And if you can't see it, I apologize. It's bad, but it's where I am right now. Okay, sorry. Okay, so let me start with the first part of this talk, which is, what do we compute? Okay, so what does the output of a solver produce? Well, I mean, it produces a satisfying instance. That's just what you did, right? You were solvers for me, and you produced satisfying instances. And you didn't produce any particular satisfying instance, you just produced anything you wanted, right? Now, these are black box algorithms, and if you've taken a course on SAT solving, you probably know there's some pretty sophisticated algorithms out there. They work quite fast, which is why we're able to use these in an industrial setting. But if you read, for example, Daniel Jackson's book, he makes a much more refined claim. He says, look, the tool selection is arbitrary, but in practice, you tend to get small instances. And this is useful because small instances are likely to be the pathological ones, and therefore they're likely to expose subtle bugs, right? And if you think about it intuitively, it makes sense, right? That makes sense. And remember, our whole process here is one of exploration and understanding. So I want to be able to expose those pathological instances so that I can then articulate properties and try to understand my systems better. Okay? Small is in terms of the number of objects that are going to be shown. Roughly think how many things I'm going to see on screen. That's a good enough proxy. Okay? Okay, good. So we said, look, why don't we actually turn this into an algorithmic question? Okay, so we worked on this line of work that we call principled model finding, which is the output is not just going to be a instance that satisfies the formula, but it's going to follow some richer property. Okay, so I'm going to spend 1 slide doing a little bit of academic bragging, and that's okay because I'm then going to cut off, knock myself down for the rest of the talk. Okay, so 1 slide of bragging is we built these systems. We built a system called aluminum. Okay, there are going to be some bad metal jokes here. I apologize. Right, so we built a system called aluminum, right? We put the min in it, so it produces minimal instances and gives you a principled way to do exploration of these models. Okay, we built a system called amalgam. And amalgam lets you look at the provenance of things and understand where things come from. And one of these won a best paper award. Okay, there's the academic bragging part. Okay. But then we read the papers we wrote a little bit more carefully, and here's what we were doing. We were saying things like, the aluminum paper says a user can be confident about every tuple, something, 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 right? Now, of course, there's a mathematical meaning for that, but we were talking about users and confidence, and those are human sentiments, okay? And you look at the amalgam paper, it says it's crucial that the tool empowers users to understand scenarios. And, well, empowering users is a statement about humans. And, hopefully in an HCI thing, you're all like, hey, Shriram citation needed, right? Like Wikipedia, right? And so we said, well, maybe we should go and study that question. And so we wrote a 3rd paper. And this paper did not win any awards. But to my mind, it's a much more important paper than the previous 2 papers. Because here's what we found. Let me show you. I am not in this talk going to give you all the details of the breakdown of the studies that we did. I'm just going to gloss over them because if you want to ask me, you can ask me about the audiences and how we gather data and all of that stuff. But we looked at multiple different scenarios, multiple conditions. We looked at minimality, maximality, some other mathematical things called unsat cores and so on. And we did things with student subjects. We did things on Mechanical Turk. So we did a whole collection of these studies, and it wasn't good. So let me explain what happened here. So here's one example of a condition we studied, which is we're going to look at reference counting as a garbage collection technique. Okay? So reference counting is fine. It works pretty well, except if you've taken a PL class, you've learned that reference counting doesn't always work. In particular, it fails if you have cycles. Okay, so we were trying to get students to understand that problem by exploring the output of alloy instances. Okay, so here is an example of a state. You have a heap, you have a stack, you have a bunch of heap cells, and there's a bunch of cycles over there, right? That's the bad state you want to get to. And after a while, the program gets into this state where now the stack is pointing to a heap cell. There are all of these cycles that are not going to be garbage collected. Okay? So that's fine. There's a little bit of detail, maybe unnecessary detail on the screen. Now let me show you what the minimal instances by the minimization algorithm come out to be. They come out to be that. That's much nicer if you have previously seen the states I showed you, but if you see just these states, to go from this to understand the problem is actually quite difficult. Okay? And you don't have to take my word for it, because here's what happened in the study. We gave students the choice of working with our nicer algorithms or working with the original tool, and most of the students actually dropped out of the study and insisted on going back to the original tool that does not produce these nice, sophisticated, principled model finding outputs. Ooh, that wasn't so good. That was kind of a blow to the ego. But what's even worse is not only did they not like it, the students who actually continued to use the tool ended up making the wrong edits because the minimal instances misled them onto what the problem actually was, right? So this is like a complete disaster, in other words. Users didn't like it, and the ones who actually persisted with it got actively misled by the tool. Okay? So again, I can give you all the details of the study, but it doesn't matter, right? This is embarrassing and this is not good. So this was extremely humbling. One of the insights here for us was, you know, as a person with a mathematical training, it's like, oh, minimal, like this is good stuff, right? This is the stuff that makes mathematicians salivate, right? But the reality was, when it came to actually building tools that were useful for the users, this turned out to be exactly the wrong thing to be building, right? So now, of course, like all of our papers are full of this, right? I mean, you open like any POPL PLDI proceedings, and the first page is always full of statements like this. So I don't know, maybe more of those things need to be validated.
So I guess on the previous slide you mentioned that, I mean, you thought it was useful that you went from the larger alloy instance to the minimized thing, and like that seems like a good insight. I mean,
in retrospect, right? So that the problem was that was an insight I had in the process of designing the talk. Yes, yeah. So in fact, I now have that. So I'm actually, to be honest, I'm giving you the worst case. There were some successes, like the provenance stuff was actually somewhat useful. So it wasn't the unmitigated success I'm making it out to be. But for me, it was more useful as a scientist to assume that everything was pretty bad and use that as a principle for work going forward than say, oh, no, like one thing was bad, but other things were cool. But I think we now know a lot more about how to design these systems better so that we end up, you know, for example, doing exactly what you said. Start with semi-maximal instances and then collapse them down and help people go back and forth between them. And this go back and forth is going to become irrelevant in the next part of the talk. Okay? So great point. Okay, so this was in some sense the starting point for me to start thinking about what do human factors and formal methods have to do with each other. And it can't just be like living in the world of algorithms and proofs and theorems and, you know, implementations, but we also have to think about how these tools work for people. Okay, so that was the point of departure for the rest of this talk. So let me now talk about the what to show part. Okay, so what is our goal when we put up these pictures? Right? I mean, I showed you these pictures of like states and diagrams and all these other things. What is our goal? Well, our goal is of showing, in this case, visual output, is that there's some intended cognitive impact. I want you to see this, and I want something to happen in your brain that helps you form a correct conception of what is going on in the system that we're modeling, right? And when you put it this way, of course, you realize, like, we're not the first people to think about these things, right? There have been decades, like literally decades of people thinking about these in perceptual psychology and in educational psychology. And so we've been trying to import some of those insights into our work. Okay? And there's, in particular, a very, very nice line of work from perceptual psychology that started off in about 1955 and has gone through a whole bunch of different papers. This paper by Dan Schwartz, by the way, Dan Schwartz is a person who works at Stanford and has done some really cool work in this area. So if you're interested in some of these things, part of the reason I'm putting up these titles is go read these papers. They're wonderful papers. I enjoyed reading them. I learned a lot from them. And you might enjoy them too if you like what's about to happen in the talk. Okay? And you can see where this work comes from. All right, so before I tell you the principle, I'm going to give you a concrete example, okay? So here's what we're doing. We are going to study a model of a society of blobs, okay? And I'm going to show you some things that are true of blob society, and you're going to tell me what you think, tell me what you learn about blobs from looking at these, okay? So this one, I'm afraid, is intensely visual, but here is an example. Here's a dinner party. We have a blob that cooks a meal, another blob that cooks a meal. Okay? What might you infer about blob societies from this output? Come on.
Blobs collaborate.
Blobs collaborate. What else?
Communist.
Sorry?
Everyone has to contribute.
Everyone has to contribute. Okay, very good. Other things? Yeah, okay, yeah, sure. Yes, thank you. Wonderful. Yes?
Blobs cook the same meal.
Blobs cook the same meal. Aha. Anything else? Anything else?
Parties need more than one blob.
Parties need more than one blob, and not a party without just one blob, yeah?
They like to cook.
They like to cook. Okay, good. Okay, so now what I'm going to do is I'm going to now juxtapose this with a second instance. Okay? So now I have a parent, it may be hard to read, sorry. That's a parent-off relationship. Okay? So question is, does this revise any of the beliefs you had about blob societies before? Or does it augment? Any additions, changes? Families cook together. Anything else?
Familial relationships are not essential to having a valid party.
Yeah, so because the first picture is actually telling you something that the second picture is potentially misleading you into believing, but the first picture actually invalidates, which is you have to have a parent-off relationship to be able to cook. Right? Okay, so you can start to see we're sort of inductively deriving some facts about blob society. Okay? Now, you might be like, I'm not that interested in blob societies, and that would be okay. But remember, these are the same tools we also use to help people understand the security postures of their policies, right? You go into a company, you've got like a network policy or a security policy, and you're trying to understand the policy, and it's like thousands of lines of code, and you're trying to understand it by looking at scenarios and trying to understand, right? I want you to think like that's the domain where we would apply exactly these same tools. Okay? Now I'm going to show you a third example, but this one's going to be a little special. Okay? Remember, when we started out the presentation, the talk, I gave you some problems and you gave me examples of things that satisfied the formula, right? A thing you did not do was to give me non-instances, right? Like when I said A or B, you didn't say A is false and B is false. You would have felt very silly doing that, right? And SAT solvers are tools that give you satisfying instances. What I'm going to show you now is something that is not a valid blob dinner party, okay? So here is a third situation, and this one is not a valid dinner party. Now, does this revise your beliefs in any way? Anyone? Back there? Do you have a hand up? All right.
Do two blobs have to cook together, maybe?
Do two blobs have to cook together, right? So this suggests that maybe it does. There was another hand up over here. So, same thing, okay? Other things? Any other statements? Any other observations?
The parent has to cook.
The parent has to cook, yeah, that seems to suggest the parent has to cook for the child to be cooking, right? Like supervised cooking, right? Okay, so as you see this negative example, you start to learn more things, right? Now, there's a technical question that some of you might have, like, hey, Shriram, I thought you have a SAT solver and this is like a non-instance. How do you do that? I will take the technical questions offline if you're interested. How do you make a SAT solver produce non-instances? Okay, but where do these examples come from? This example comes from a theory of the principle of what's known as the principle of contrasting cases. Okay? And in contrasting cases, generally what this theory shows is that people learn better when they see multiple systematically related examples. Okay? And another part of the theory tells you that it's also useful to show negative examples. And the intuition you can think of is as you show positive examples, you sort of build out the space in your head, but you don't know kind of what the limits of the space are. And the negative limits put edges on it and curtail the space inward. So you sort of push outward and push inward, and you get a much better sense of the space of the thing you're looking at. Right? And you kind of did exactly that for me, right? You notice that when I showed you the negative examples, you were able to come up with new things that you did not come up with when you only saw the positive instances. Okay? So this is one condition where we look at 2 positive and 1 negative on screen at a time. We tried a whole bunch of other conditions as well, multiple domains, again, crowdsourcing and student subjects. We use prolific in this case. Generally, what we found is the multiple instances was not very useful, but the negative instances were very useful. Right? And that's like a direct contribution from the theory of contrasting cases into improving the output of formal methods tools. Okay? We actually found one condition that was even more useful than the one I showed you, and it's this condition where I have a plus plus and a plus minus, and what that means is, think of it this way. Have you ever tried to compare maybe 2 pictures or 2 documents and you put it on adjacent tabs and you just go flip back and forth? Ever done that? Okay, right? Because again, what are you doing? You're using your visual cortex to it's got locality and you're trying to exploit that ability to localize things and look for the differences, right? That's what this condition is. This is a condition where you have a positive instance, but you can click on a button and it turns into the nearest negative instance. You click on it again, it toggles positive, toggles negative, toggles positive, toggles negative. And we saw people toggling up to 7 times, going back and forth, trying to understand this edge case over here, right? And this is actually something I haven't seen much in the literature before, because a lot of literature in contrasting cases doing things like science education, which is done on paper, so it's kind of hard to make people do a flip. And here we're using the fact that we have a computer that we can provide a toggle button that works instantly, right? So again, this is a thing where we're actually trying to use the theory, make predictions from the theory, and actually building, hopefully improving the tools as a result of working with the theory, okay? So my takeaway message from here is I'm actually going to present this takeaway message a little bit snidely, which is that this is basically like the wheel as reinvented by computer scientists, right? There's a whole theory of wheels, and we'll just we'll just hack our way together, and we don't need to know anything. Now, what can anyone else have done that's potential value to us, right? And I think there is actually a lot of value. We're trying to have a cognitive effect. There's a whole bunch of theory out there that we could bring to bear that has to be tested in context, but can potentially provide insights that we don't have ourselves. Okay? Okay, that's the second part of the talk. The third part of the talk is how do we show things? So now we're going to play a game, all right? I am going to show you a picture, and you're going to tell me what domain of computer science the picture comes from. All right, ready? Good? Okay, so here's a picture. And it says fork, fork, philosopher, right fork, left fork. Yeah, we're good? Yes? Okay, good. Okay, so this is a dining philosopher's problem, okay? And in fact, there's here's a pre-state, and then there's a transition, and there's a post-state. Can you see the differences? Anyone? Anyone? Where are the differences? Bottom right-hand corner. And any others? Yeah, left side. Okay, good. Okay, so there's a pre-state and post-state, and forks are moved around a little bit. Okay? All right. And part of our goal here is, I also have sort of an educational goal here, which is, if you think about dining philosophers in operating systems textbooks, well, dining philosophers is a dynamic problem. But your operating system textbook is always a static picture, right? And what if we could give you an active textbook, right? So we can actually embed dining philosophers, let you flip through, understand it, maybe make some tweaks to the policy and see what happens, et cetera, right? So wouldn't it be so much better if your textbook had this picture in it? You look a little skeptical.
It's already too complicated.
Okay, well, fine. What do you want it to look like instead?
3 philosophers.
Come on, man. It's only 5 philosophers. Would this work? Would this be a better textbook presentation? You want a diff. You might also want that. Yeah, okay. Now you're okay with 5 philosophers, right? See. Okay, and now pre and post. right? You're right. The diff is actually a very valuable thing, and that's something we've been exploring is when you're doing temporal sequences is thinking about how to show the diffs, okay? We've tried some initial experiments. The things we tried didn't work out. We thought they would, and they didn't work out. So we're still in the process of actually being able to show the diffs because people do actually do a lot of reasoning about differences rather than about full objects, okay? So even without that, I think we can all agree, like I haven't done a user study, but I think it's pretty clear, like, you know, the thing at the bottom is better than the thing at the top, right? In fact, it's the same information, right? Like literally, it's exactly the same information, and yet something is working about the picture at the bottom, okay? We'll get back to that in a moment. Let me show you another picture, okay? So this one says ciphertext, public key, private key. What domain are we in? We're clearly in some sort of crypto, right? Like, okay, see, now you're happy. There's something for everyone in the room. Okay, all right? Okay, but except that's probably how you draw your crypto protocols, right? Okay, swim lanes, Alice and Bob pictures, I don't know how you like to call them, like any of those names. Exactly that. Okay, so where are these visualizations coming from? There's a tool we've been building called Forge. Forge is basically our improvement on Alloy. And in Forge, we let you do these domain-specific visualizations. We're working on a whole bunch of infrastructure to make it as easy as possible to build these. And I'll tell you a little bit more in a moment what that means. But the previous one, the Dining Philosopher, is about 100 lines of code. There's a version of this you can get in about 100 lines of code. This one is actually an interactive picture, so you can click and hide and like ask questions about it. So, you know, about 1,000 lines of code gets you a pretty nice visualization, an interactive, queryable visualization of a crypto protocol. Okay? But I claim there's something much more going on than just pretty pictures. And to do that, I'm going to do a little test on you. Okay? Now, again, people who studied CogSci will be like, oh, yeah, my professor's done this to me 3 times before. Those who haven't, especially like formal people, hopefully this will be a little bit of fun for you. Okay? So here's the task. I'm going to put up some text, okay? And you're going to tell me what color the text is. Ready? Yes? Ready? Okay, go. Where is the rest of you? Okay, let's try again.
Green, red, orange, red,
Blue.
red, blue, green, black.
Okay, so you notice you're getting a little slower. So what's going on? This is, as some of you already know, this is called a Stroop effect. And the Stroop effect is basically that your reaction times are proportional to whether the thing is congruent or incongruent. So when I show you the text, there's 2 channels here, the text channel and the color channel. And when the text color and the color channel are congruent, your response time is much quicker and you're more accurate than the incongruent. Okay? Now, you're like, what does any of this have to do with anything, Shriram? And I will tell you. So I'm going to show you one more domain. Okay? So I'll read this out to you, maybe hard to read. It says farmer near, fox near, chicken far, and grain near. What's that sound like? Yeah, constraint solving or river crossing puzzles, right? Okay, so here's another representation. Okay, maybe it's a little prettier. Okay, so here's a pre and post state. Now, why am I talking about the Stroop effect? Because if you look at the visualization at the top, right, the fox and the chicken are on opposite sides of the river, but they're on the same side of the picture. Because it's a generic visualizer, it doesn't know about any of these things. So it puts them on the same side. It puts the farmer and the grain on opposite sides, good, but it puts them at the same positions on both pictures, even though they're flipped sides over here. Okay? Now, you might be like, okay, Shriram, that's because you built a really stupid visualizer. Now, here's why the visualizer does that. Previously, the visualizer used to do a random placement of objects, and that's great because it's going to avoid this problem. What that does is it keeps moving the objects around. So your visual cortex is, as we said, you know, we talked about flipping things back and forth, right? You have this like persistence of visual memory when you look at something and you go to the next state and everything is moved around, and that's really bad too. Right? So there was actually a cognitive principle behind putting things in constant places, but that's now creating a different kind of problem. In fact, the first time I saw this output, like my head is hurting trying to understand what's going on. Like, where are things? Why is the left on the right and the right on the left? Okay? So there's actually something more than just the prettiness of the picture here. The thing is, there is important spatial information that is not being encoded in the generic visualization. Here, leftness and rightness are really important, right? Think about the Dining Philosopher. part of what's really confusing, and the reason you want me to go down to two philosophers, is because there's critical spatial information. Left and right fork are actually really meaningful, and the placement of the philosophers is meaningful. That's spatial information. If you think about the crypto picture, well, there's spatial information like Alice's swim lane and Bob's swim lane. Like if I want to look at Alice's things, I want to be able to project out of Alice, right? But there's also temporal information. Like just imagine a crypto protocol where I said, oh, time, what's time anyway, right? The thing is, it's really important to look at the sequence of those messages across time because there's, a partial ordering across those messages, right? So the generic visualizer doesn't know anything about space or about time. And that's one of the reasons why these pictures are so confusing and so hard to work with, right? So what we've been working on is, there are visual metaphors that have been developed by domains because they found them useful. Also, if I want to show something to a cryptographer, they've got a language and there's a reason they developed that language. So that's part of the story, right? Is work with the metaphors of domains. But I think the even more important thing is not, sure, that is a very, very, very sweet looking chicken and you wouldn't want any harm done to it, right? But more importantly than that, we have to respect these spatial, temporal, and other relationships. And so what we're working on in Forge is a way of being able to very concisely state those things, and then the visualizer can use that even if you don't have pretty pictures, because then we avoid doing things like Stroop effects on users. Okay, and the last step we're looking at is also building domain-specific input languages so we can create these epistemically closed, like we have a crypto protocol description language. So you don't have to know anything about the alloy syntax and SIGs and braces and all these other things. You just write a crypto protocol, you get a crypto protocol output, and you stay inside that domain so we can start taking these tools into different domains like distributed systems and cryptography and so on. Okay, so that was the third part of the talk. So we talked about what to compute, what to show, and how to show it. And last part, I want to talk a little bit about how to describe systems. Okay? So I'm going to focus on one specific subproblem, which is a logic called linear temporal logic. So many of you have heard of it. Some of you have not. Let me introduce you to it. I start with propositional logic. And you all know propositional logic. And how do I know you do it? Yeah, because you were my SAT solvers, right? Wonderful. So that's propositional logic. But there are things that are impossible to state in propositional logic, like, eventually I'm going to get a green light somewhere. Or it's never the case that I'll have both a green light and a red light at the same point in an intersection, right? Or if I acquire a lock, I'm eventually going to release the lock, right? Or if you have like a kid at home, then you might have a policy like no cookies till you finish your homework, right? So you notice here that I've got some propositional variables. I've got some propositional operators. The underlined things are temporal operators. Okay? So linear temporal logic is you take propositional logic and extend it with like roughly 4 temporal operators. Okay? Now, linear temporal logic is used all over the place. It's like a classic logic that's used in computer-aided verification, but it's also gotten very popular in synthesis and in robot planning. Right? So in fact, people who do robot planning with RL have found that linear temporal logic is a particularly nice way of stating policies. So there's now a much bigger domain of people who now need to use and have begun to use linear temporal logic. Right? And there's, again, like there's, if you are a verification person, you know that like classic papers like, Moshe Vardy's, branching time versus linear time, the final showdown, and what is CTL? It's a language that's unintuitive and hard to use. And in contrast, linear time framework is expressive and intuitive. Oh, this sounds like kind of some claims we've seen before. The temporal logic sugar, this is like wonderful logic that comes out of IBM. It's like easily and intuitively specified designs. Okay, so, citation needed, right? Okay. So we decided to investigate this question, and to be honest, I'll tell you what the motivation was. So motivation was, my colleague Tim and I went to a robotics talk that was using LTL. We're like, look, I don't know anything about robots, but I know LTL, so maybe from LTL I can learn something about robots, right? So we go to this talk, and the speaker starts with an introduction to LTL. And there were some grad students in the room who were also using LTL, and the speaker makes a mistake in their presentation of LTL. The speaker doesn't notice it, the students don't notice it, and everyone's like, wait, how are all these people working with LTL? What are they working with? If they are making mistakes and don't understand, like maybe we should investigate this more. That was actually the starting point for this work, okay? Well, so what does it mean to use LTL correctly? I would argue that it means 2 things. One is, given an LTL formula, can you correctly translate it into English? And the other is, given an English statement, can you correctly translate it into LTL, right? And I would argue that the second direction is particularly important because if you're going to do verification, or you're going to do synthesis, or you're going to do planning, or any of these things, there's some utterance in your head, I would like the following thing to happen, right? And I have to translate it correctly into LTL because the tool is just going to go off and do whatever the LTL says, right? It's not parsing English, it's parsing LTL, okay? And if you know something about these logics, you'll actually say, actually, Shriram, there's two parts to it, right? Because this is the syntax. The question is, there's also a semantics layer, and there's something called trace satisfaction, and it's like infinite traces and so on. So there's actually two parts. There's really three things you want to study, right? Because if somebody makes a mistake, are they making a mistake in the syntax, or are they making a mistake in the semantics? Okay? So there's like three conditions. Again, I'm leaving out the details of the study, did this over 3 years. We also got like 30 researchers, active users of LTL to participate in the study. They didn't do a whole lot better than the students, unfortunately. So you can sort of see where this might be going. What we have as a result of this 3 years is a catalog of the misconceptions that people have about LTL. And let me show you one of them, okay? So this thing that we call the exclusive view misconception. So quiz for everybody in the room. When I say X until Y, do I mean, I'm going to give you two options. Option one, there's some time t, X is true until time t, at time t, Y becomes true. Option two, same as the above, but at time t, X becomes false. Okay, let's vote. How many of you vote for option number one? How many of you vote for option number two? Oh, interesting. Okay, good. Why? Let's take somebody who voted for option number two. Why did you? Because it's clearly the winner. Why did you vote for option number two? Like there's something went through your head, right? Some intuition went through your head. Like, did you? Yeah.
Well, it seems like it's not, the proposition isn't useful unless it becomes false.
Doesn't seem useful, right? Like, did anyone work through maybe a concrete example?
Like I eat until I shower.
Yeah, exactly. Eat until I shower means you probably are not eating inside the shower as well, right? That would lead to some soggy results. Okay, or let's take our robot friends, right? So if a roboticist says the robot's motor is on until the robot reaches the destination, well, clearly we want the robot to turn off its motor at the destination. Okay, and of course there's like three people in the room who are saying like, no, because in fact the correct semantics is one. Okay, now, I'll just point out, like, here's another sentence, right? I don't eat cookies until I eat my room. Doesn't mean that the moment you clean your room, you eat the cookies. Now, that might be true in practice, but that doesn't mean necessarily, right? So I can even construct alternate sentences where, like, it's not so clear what should happen, okay? In the misconception literature, this is closely related to what is called a vernacular misconception in the education literature. So vernacular misconception is basically we take a word from the English language and endow it with some very technical meaning. Right? And we do this because we think, hey, this will make things more intuitive and easier to understand. But the problem, of course, is it has sometimes exactly the opposite effect because we bring all the baggage of the vernacular in as well, and that's not actually accurate. Okay? I mean, the thing is, I actually think number two may be a better interpretation. Okay? It may be a safer interpretation, but the point is that is not how LTL is defined. So we did this study. And remember, there were three conditions we were studying and three situations we were studying. People generally did well going from LTL to English. This was one counterexample. People had a bunch of trouble with the trace satisfaction part, and this was like really bad. And just remember, this is the important direction. Okay? So this is worrisome, disturbing. To me, the takeaway messages are, first of all, I think there are very serious implications for people building tools that take things like LTL, because the assumption has always been, well, the user will state exactly the right thing and that the tool will execute exactly what they say. But if people don't know what they want or they're not stating it precisely, then what are we going to do? What's the tool actually doing? Okay? The second thing is we've also built a bunch of now validated tools for users. We have some universities to teach LTL that are using our tools to improve the LTL education. Essentially, these are all multiple choice instruments. It's something called a concept inventory, if you know what that is. And if you don't, basically it's a multiple choice instrument. You can even give it like with a clicker in class. And so if a person picks a particular wrong answer, so there's like one correct answer and three or four distractors, the thing is each wrong answer corresponds to a particular kind of misconception. So if I administer this quiz in class, right, and you all pick like option number 2, I get, aha, if 30% pick option number 2, I know that 30% think the following incorrect thing is true. I can address it immediately in class instead of letting that misconception linger. Okay? So we have this validated tool, but we also have ideas now how to better design these logics. Right? We have ideas of what these operators should look like. I'm now of the belief that we should not have an until operator. We should have 2 explicit until operators corresponding to interpretation 1 and interpretation 2, and there's no default until operator. Right? So we have ideas about how to better design logics, but even better, we have a methodology, a human-centric methodology for designing these logics. So the next time somebody designs a logic, they don't have to put words like intuitive in the title and stop there. They can actually validate these claims, and maybe even better, design from humans up rather than, design something and then hope the user study succeeds. Okay? So those were the 4 parts of the talk. So as a reminder, I talked about what to compute, and I said we can build these very principled algorithms, nice algorithmic techniques, but they failed miserably. There might be a better way forward, like where we, use those insights in more interesting ways. The second is, what do we show? I talked about the theory of contrasting cases, multiple examples, and negative instances. The third was, how do we show it? And I talked about domain-specific visualizations, but in particular, using the spatiotemporal properties to improve the quality of visualization and improve the ability to understand them. And finally, there's a whole bunch of work we still need to do in the design of these logics and languages and so on for describing systems and verifying them. A few other things that also excite me in the space, I've been thinking about the education question of how do we get people to even learn how to write properties? How do we motivate property writing? How do we design new type systems? Or how do we take sophisticated type systems that already exist and explain them better to users? And for this, it's wonderful that Will cried, because this is all Will's work. If you're learning Rust, I would strongly encourage you to look at rustbook.cs.brown.edu. Will's done a ton of work on this, validated improvements to the learning of Rust. How do we find and fix PL misconceptions? So there's a whole space of problems here that sit at the intersection of like sophisticated formal methods and humans reasoning about and understanding and learning and using these things. Okay. So my training, as Manish said, I come out of sort of a mathy, algorithms-y, semantics world, and out of like a programming languages, software engineering world, right? Like sort of the top and bottom bubbles. And over time, I've realized the importance of the cognitive science bubble and trying to bring that into the loop. The education bubble, you might think, it's a little more controversial because I'm going to make like a radical claim here, right? You might be like, oh yeah, he's a professor. Of course, he better be thinking about education. It'd be nice if more of our professors did, right? But I'm actually going to make a much stronger, much more radical claim. My strong radical claim is that everybody who builds a tool is in the education business. And what I mean by that is we are producing output for our users. And I don't mean like you're producing output for students. You might be producing output for, the most advanced programmers in the world up in Silicon Valley, right? The thing is, the tool is producing output. The intent of that output is that the user will see it, read it, hear it, whatever, and understand it and learn something about the system. Right? When a compiler gives an error message, even when a compiler gives a syntax error, right? It's trying to tell you something. It's trying to teach you something about the formal system that you're working with and about the artifact that you produced, right? 2 things at once. Your program contains a type error means I have to understand something about my program and I have to understand something about the type system in combination, right? So we're all actually in the education business. And that's why I think every one of these tools could benefit from knowing more about theories of education and like results in education and bringing them to bear. And that's why I have this full cycle loop over here. Right? If you're interested in learning about formal methods, or if you teach about formal methods, I would encourage you to take a look at Forge. It's early stages. It's still only about 3-4 years old, but we keep building up. We're working on a book to go with it, etc. But we think there's going to be like a really nice system out there for people to use. And finally, if you want to reach me, here's how you can reach me. Okay, that's the end of my talk. Thank you very much for your time. I will take all of your bouquets and brickbats, especially brickbat, because those are more fun. Yes?
Talk a little bit more about how that system sort of takes these there's constraint systems and turns them into more domain-specific visualizations.
Yeah.
I don't know how you abstract away, the domain, which is very important there. Like, give the right building blocks to build these custom visuals.
Yeah, good question. I wish I knew. What we're working on, what we are planning to do. So right now, all we do is we sort of think roughly like a DOM to work with. Okay, so it's not very sophisticated yet, right? But what I really want to be doing is we have the ability, since we're building our own system, we're no longer working with Alloy, right? Forge is starts with Alloy, but it's its own thing, right? I want to start thinking about how we can, when you write a spec, right, you can actually state spatiotemporal properties in the specification, right? So we're going to blur the model view distinction a little bit, because right now it's all models completely separated from the view. But if we take some of these properties, we can encode them in the model because they are semantic properties of the model, then the view side will inherit all that information and be able to use it for initial placement decisions, right? So for instance, my dream would be we can get to the pictures, the prettier pictures that I showed you, but they won't have any of the prettiness. There won't be a round table, but the spatial locations will just be rectangles, right? There won't be a chicken that looks like a chicken. It'll just be a box that says chicken, but it'll be in the right place. When I look at the edges in the crypto protocol, there won't be a beautiful blue arrow, but there will be something telling me something about directionality and time position, and it'll be like I can reorder by time, right? Or I can reorder by space. That's where I want to get to. We have some ideas about how to modify that into language so that we can convey that information down to the default visualizer and get a default. Does that make sense? Wonderful. Thank you.
Are you saying you enrich the semantics with some notion of topology or geometry?
That's essentially what I'm saying. Yes, that's right. Right. And we're still working on some designs for how to do that, but that's what we want to do. Absolutely. Yeah.
I wonder if you have any thoughts on the controller side of things. It seems like with this sort of dumb visualization, it's pretty easy to synthesize controls that would respect the invariance of the model.
Yeah.
But once you make the visualization much more sophisticated, now I'm not sure if I can drag the chicken and still maintain those.
And that's actually the tricky part of that question, right? Is how much semantics do we put in there? So right now the visualizer, it's a tool called Sterling that my postdoc Tristan Dyer built. So right now the visualizer is sort of pretty spring models and things like that, right? It's not very interesting, right? The question is, how do we convey enough semantics to the visualizer to even know what is a valid thing you can do? For instance, I want to do projections, right? Like we want to do semantic projections, right? So I want to do a spatial projection I'm just focusing on space and time right now because that seems pretty fundamental. But how do I do a spatial projection or how do I do a temporal projection? And I need to know enough about the semantics of the domain there to know which ones are valid and which ones are not. And that's the information we're trying to capture right now. Okay, so I don't. Basically, you're saying, Shriram, you didn't really answer my question, and you're right. I don't know the answer to it yet, but that's where we're trying to go. Yeah, and I'd love to hear more. Like, if you want to give me, here's a challenge example or something, I'd love to hear that too. Yeah.
You mentioned that the minimal model people did not learn much from it, but negative cases, etc. But what about things that are just beyond the minimum? Just illustrating the inductive step, does it lead?
Yeah, that's a great question. This is my dream. Is someday I would like to be able to mathematically characterize that middle model, right? Maximal models are bad because it's overwhelming. Minimal models we've demonstrated are bad, but there's something like a 2 or 3 steps above that seems to be right. And in fact, sort of related to your question, it seems to make sense to maybe start there and then minimize and say, this is the essential part of what you saw. That's where we want to go. I don't have a good. The thing is, I've spent a lot of time breaking my head over that question for various domains, and I can give you a good answer in a domain-specific way, which of course doesn't generalize. And I'd love to be able to figure out what's common to those, so I can bake that into an algorithm, and then we're good to go. I don't know. I wish I did. Yeah. Does that not answer your question? Yeah.
Going back to the contrastive.
Oh, contrastive cases. Yes.
So in many real world situations, there are lots of dimensions along which things can contrast.
Yeah.
So how do you choose what to show? Because that can also get quickly overrun.
Yeah, no, that's a great question. We are in a very generic world right now. I think the end goal is, in some sense, it's sort of the same answer I'm giving over and over, is we have to embed more of the domain semantics in. Right now, we're in like this, what logicians call uninterpreted symbols, right? Nothing means anything, right? And that clearly isn't working. Right? But also, I think if we can add more semantics in there, it's funny because, it's sort of ironic for me to be saying semantics because, this is a semantic description, right? We are writing semantics, and yet somehow it's not useful semantics for answering these kinds of questions.
Well, you're not writing about the spatial semantics.
Right.
Which is maybe the issue.
Right. Like, for example, right, this thing says that an answer, that a child, say a node has a left and a right. But we haven't said what left means and what right means. And that's why, in fact, if you look at the picture, sometimes it flips left and right, or it fails to have one of those, et cetera, right? So you're right. And so right now, when we talk about contrasting cases, it's all relative to like these uninterpreted universes. But if we start adding more interpretation in here, then I think there's the potential to do something much richer in the contrasting cases. Because also, the theory of contrasting cases tells us that they have to like contrast in systematic ways. And our systematic right now is just like, like logic systematic. Yeah.
Well, related to that, what
Yeah.
your examples made me think of is, I think ultimately what people want are causal models. But a lot of the variables or a lot of the dimensions won't be really causal.
Yeah, that's right.
So
that's right.
That's right. That's maybe what
that's yeah. Like, well, I think here's a way I'd characterize my non-answer to you. We have for many years worked with like alloys like a fixed point, and we were just working on our own tooling. Now that we've made a break from it, we're free to like change the language to incorporate all of this. And now we're really like asking, what can we now do now that we own the language ourselves, right? Yeah.
I just want to ask you a bit more about what you said about role in the education business, because I think that's a really important point. And just for context, others, everyone, I'm Joseph G. Williams, so I'm a professor in human interaction, artificial intelligence, psychology, statistics, and education. And Shriram, what you said is actually really
From Toronto, by the way, the opposite corner of the continent. So we're very lucky to have him here. Yeah.
So what you said is a really good point. And if you think about it, right now, you're educating me and I'm educating you, right? Every time you say something to someone in an email, I'm teaching you something.
We hope we are.
That's a great point, actually. Yes. I hope to teach you something.
Yeah.
And we're also doing behavior change.
Yeah.
I'm hoping that when I say something to you by email or now, it might make you do something differently 5 months from now.
That's right.
So I think
in my case, I'm hoping you'll reply to my emails, but yeah.
I'm writing an email right now. So I guess my question is, maybe we should use a different vocabulary word to indicate this. It applies to what you said about anyone who builds a tool is teaching and learning. And also we should put more responsibility on tech companies. Tech companies give us TikTok, Instagram, whatever, and then say, to hell with you. They make us responsible for figuring out how to use their apps. And I really think if we had a word for this, that was not learning or education, it could actually help generate some activity. Because if you think about it, when I say learning, you're like, oh, school. Right?
Yeah.
What is it?
Yeah, notice I had to work so hard to say I don't mean education the way people normally think about education. Yeah.
So if someone does languages, what is the word, or make up a word now, hashtag whatever, right?
Yeah.
Make up law, right?
Yeah.
But what is the word for when I talk to you, even in a sentence, I'm trying to hopefully teach you something and get you to change your behavior. What's that word? Or you
I know. Will answer the question for me. This is why I hate it. What's the point of
you all have ideas, please. Give a word. What's that
no, I think this is a very good insight, right? It's like I have to struggle to explain what I mean by education is not what we conventionally mean by the word, and that sort of educative interfaces of some sort. Yeah.
I mean, maybe someone is like, let's use a sentence, right? I'm hoping that you X from my conversation.
Yeah.
What I said did X.
Right.
Like, what is X? Is it
What's
like
X?
change you?
I feel like social psychology likely has terms for this. I don't know what they are, but this definitely feels like.
Yeah.
I published in social psychology.
Okay.
One thing you would see, that's a good idea. I like that idea a lot, but I think that, I was on the sidetrack, but I think that learning is almost invisible. If you talk to social psychology.
So tell you what, here's what we're going to do. I believe there's a break after this. So we're going to argue this over break. So everybody is interested in debating this point. Let's gather up over this because I don't want people to be stuck.
We're going to give them lunch for free. Could be
I thought you'd buy them a cookie or something at least, but okay. No cookie. I'll buy you a cookie okay, good. Okay. So, any other questions before we break up? I know we're running out of time, so. Yes?
Yeah, at the end you mentioned that something to aspire to would be having a human-centered design process for formal methods type tools, and it seems like you did a lot of examples of doing, I guess we'll say, good evaluations post-hoc.
That's right.
I'm curious if you know of any examples of tools that you think have been built in this good way that we could look to as examples.
I'm going to get into trouble because I'm going to end up saying no, and somebody's going to like totally flame me. I mean, specifically, I'm thinking narrowly, right? Obviously, there's lots of like all the stuff that people in this room do, but there has been. You know, it's actually interesting. I found one of the LNCS. There's something like LNCS 11 or something like that, right? Well, like prehistory. There's a book, it's the volume on compiler construction. And it is kind of shocking that like about a seventh or maybe a sixth of the book is about the quality of error messages. And a very detailed deep dive into error messages. And I finally found, it's very hard to find, but I finally found this book in the Dagstuhl basement and like photographed it with like my CAN because it was like how awesome it was, right? So it was actually the case that, you know, if you go look at like some of the early PL, some of the early Pascal kinds of systems and things like that, people were thinking much more holistically. They were thinking like, you know, we're trying to build these things for students and, you know, we have to. But I can tell you, as I built this system called, you know, I co-built this system called Dr. Racket, Dr. Scheme. And we really wanted to make something student friendly. And we sat there, we went to labs, we saw students struggle, we would go back and edit the error messages, saw students struggle, edit the error messages. We did this for like 15 years. And then in like 1995 is where we built the first version of Dr. Scheme. In 2010, we did a formal user study of Dr. Racket, and it was a complete disaster. Right? So all of our good intentions, our ad hoc observations, our responses to all of that had led nowhere, right? So I think like more and more, I feel like with that, all these good intentions, I can talk about well-intentioned systems, but my own well-intentioned system was a disaster. So I mean, they were probably smarter than me, so hopefully they were less of a disaster, but I don't know. I can't really, can you think of, you usually are a good repository of this sort of thing. See, exactly, this is the problem, yeah. But now I can say, I can blame it on, right? So if somebody flames me, I'm like, well, couldn't come up with anything, so yeah. Good, yes?
So I mean, we talked a lot about the system teaching us things. Is there any way to have a feedback loop? I mean, because then the goalposts are moving, right?
Yeah.
With your 1 and 2 about until, what I was thinking is that people who pick 2 aren't familiar with material implication, which is fine.
Yeah.
But how do we get people to think about that? And then, I'm asking about feedback mechanisms because the goalposts are moving for how the tool should give feedback.
That's a good point, right? Like, why can't the tool educate itself in return, right? Like, you know, if for example, here's a naive example, right? I told you we have this validated instrument about LTL. Okay, so any tool that LTL is using LTL as its interface could first administer that instrument to the user to find out what they think LTL is, right? And now all of their utterances are relative to that instrument, not relative to the ground truth of LTL, right? So it could then, if necessary, rewrite the LTL formulas to automatically into an and false and this and that, right? Why couldn't we do that? I think we certainly could imagine doing that in a situation like that. Right? And that's a case where the user educates the tool saying, this is what I mean by the utterances I'm about to give you, right? I think that's a very simplistic, obviously, example of feedback loop, but I think that's also totally a direction to go. The reason I didn't say that in my talk is because that, again, it shifts the balance back to like, well, it's the damn human's job, right? The human has to take a quiz to be able to use this tool, right? It's like, it almost feels like a cop-out, like, let's just make it the human's fault problem, right? It's their fault kind of thing. And I want to put more burden on the formal methods tool people instead. I feel like we've like not done our job, and it's too easy to say, feedback, you know? So, but I think technically, absolutely, that would actually be, I think, a good thing to do in this case. Okay, I know we're out of time, so I should stop. Thank you so much for your time.